Okay, welcome everybody. This is the week 5 webinar of the online statistics class. So thanks for coming. And let me tell you the plan for today. What we'll be doing is we'll be answering any questions you have as always. Okay. And then we'll get into sampling distributions. Okay, a very important concept that sometimes a little tough to understand, but it's a really we're going to be using it for the rest of this course. So it is really important. We'll talk a little about biased and unbiased estimators, and then we'll get into the most important theorem of all statistics by far, and that is the central limit theorem. And there are going to be three different types of central limit theorem that we're going to be working with. And one of them will be the central limit theorem for means. And hopefully you know what it means to talk about finding a mean. Then we'll look at the central limit theorem for proportions. And then we'll look at the central limit theorem for sums. So that is the plan today. I want to let you know this is week 5. 5 is an odd number. So because it's an odd number, what don't you have to worry about? Hopefully you all know. Yeah, no exam this week. On the other hand, there's kind of a much bigger thing that you have to do. What's the big thing that's going to be due on Sunday? What's the big thing that you have to do on Sunday? Yeah, submit project one. Project one must be submitted by Sunday. I recommend Saturday. That way, if something goes wrong, you have an extra day. Waiting till the last day doesn't really help. So it's better to go a little early. And I want to remind you a few things. One is that if you've not already sent me a draft of your project, then if you want me to look at your project and give you suggestions and feedback and comments for improvement, then that draft must be sent to me by Thursday at 8 a.m. The earlier the better, because if everyone sends it Thursday at 7:59 a.m., then it might take me a long time to read them all. And you may not have much time to make the fixes that you need to make. That could take a long time sometimes. So I recommend, tomorrow or the next day, if you can, um, submit. And what I do is I read it out on a first sent, first read basis. So whatever gets sent to me, if three get sent to me, the one that got sent first is the one I read first, and then give you submission comments about it. A few more things important about the project. One is, again, this is a group project. You must have partners. Make sure that when you submit your final project onto Canvas, make sure that the names of the partners, including yourself, are all on the project. And that way I can give points for everyone who's in it. Okay. And it is a requirement to have partners. Okay. Two or three is what you have to have. Another thing I want to remind you of is that you're not allowed to use AI for this project. Don't even think about it. So do not just ask AI to, hey, here's the instructions for the project. Write the project for me. I will know, and I'll be very harsh on grading. So do not let AI do any of your project for you. Okay, this is supposed to be done by you all, and that's important. And I'm kind of an AI expert, so I will know. I can tell when someone's using AI, and I just secretly take off lots of points throughout when I see it. So don't do it. Got it? Okay, so that's a really important thing about the project. And hopefully you're making great progress and you'll have a wonderful project. I have noticed that those, I've been doing this project for a long time. I've been, teaching this class for a long time with the project. And those who submit the draft tend to do a lot better than those who don't. Because if you submit me the draft, I can let you know a bunch of things that need improvement and fixed. You can go fix them, and then you won't lose as many points because you'll have fixed most of the mistakes. Whereas if you don't send me the draft, then I won't know, and you'll just be sending the final project. And if you make mistakes, then you just get zapped because they're mistakes. So it's really important that you do that. I'll also be watching the Project One discussion board pretty often throughout the week. So not every moment. I don't sit there all day long on the internet. I do sleep and have fun sometimes and teach, but every day for sure I'll be looking at the project. So are there any questions at all about anything for this class? Okay, if there's no questions, then I always try and bring in like current event stuff, what's important. And so what's happening on Sunday? What's the big thing in America that's happening on Sunday? Anyone know? This is not a math question. Yeah, Super Bowl. So I thought I'd give you a little Super Bowl kind of question. Okay. Do you know how old football players, and I'm going to say American football from America players are, not soccer? You know how old they are? You probably don't. Okay. So here's what I want you to do. I want you to look up three football, so American football players, and find the mean and standard deviation of their ages of those three players. Let's see if you can do that. It'll take a couple minutes, but it shouldn't take long. You can just ask, you just go online and find three players and find out what their ages are. Very easy to ask Google, what is the age of, this my favorite player? And by the way, I know very little about football, so don't ask me, but you could ask Google. What I do know is statistics. And maybe we can figure out maybe what the average age is. Maybe not. Let's see if you can come up with it. And when you do find those three ages, put it in the chat box. Put it in the chat box. So at least we'll have a few samples. So let's see if you can do that now. And I'm going to give you a couple minutes. It takes time. But it shouldn't take 45 minutes. It should just take a minute or two. And if you don't know any players, you can just ask Google, give me three players, name and the name of three players, and then ask what are their ages. Let's see if you can do that. Because what I want to do is I want to really make sure that you understand what this is all about. And this is a good example for that. And one thing I love about stats is it's really easy to come up with current examples. So I always look, okay, what's big this week? And then I try to put something in about this week. And try to not make it too depressing because news could get really depressing. So find the ages of three players, then find the mean. And don't forget, you can easily find the mean. You can go to the calculator, and if you don't have a link, I can pop in the chat box and then you can see it. You have it immediately. And in fact, if you go to the one variable statistics calculator, that's the one for that. And then you can get the mean and the standard deviation. It'll be a sample mean, a sample standard deviation. So just in case you want that link, I just popped in the chat box. Okay, so I see three players. Now find the mean and the standard deviation of those three players, and that's what you need to put in. While you're doing that, Let me grab one more thing to get. Okay. So I'm looking for a mean and standard deviation of your three players. Calculator needs five numbers? I don't think so. Let me see. For some things it does, but not for that part, I don't think. So 42, comma, 39, comma, 31. Sample standard deviation, calculate. Oh, it's saying that. Ooh. It says it, but that's okay. You can ignore it. Just hit OK and then it still gives it to you. Do you see how it gave it? So yeah, it needs five numbers if you want a pie chart and a bar chart, but I'm not asking for that. So so you said mean was 37 and standard deviation was what? So was the standard deviation? It shouldn't be that hard. It's just a calculator. Okay. So again, you should have your mean and your standard deviation. Everyone should have a different mean and a different standard deviation. You're not using the same three players, using different three players. That makes sense? This shouldn't take too long. Takes a little bit of time to find out how old the three players are, but that doesn't take long. So what is your mean and what is your standard deviation of the three players you found? Don't see y'all jumping in, but hopefully you can get there. This isn't supposed to be hard. This is week one stuff. Just popping in the values using the calculator. All right, I'm not seeing you all come in, but I want at least a couple examples. It's taking a lot longer than I thought. There we go. All right, we got 29 for the mean, and we got 11.2694 for the standard deviation. And you got 37 for your mean. What was your standard deviation? And I believe it's really 37.3 or so. That one I can do in my head, actually, since you gave me the three numbers. 5.6862. Okay. I don't see the rest of you doing it, but we need to get moving. Okay. And we could pick three different players and three different players again and three. You could do this all day long, right? So notice, and the symbols are really important. X bar means a sample mean. So X bar means a sample mean, and S means a sample standard deviation. And we can look now at all the different sample means that could be done. So again, you could find three players, I could find three players, your friend can find three players. We could do this all day long and find three players forever, for a long, long, long time. And each time you're going to get a different sample mean. Okay? So if you look at all the sample means, that's a list of data now, sample mean data. Now, with a list of data, now you can take that data and find the statistics based on that data, which are a bunch of sample means. So this is really important. And by the way, I looked it up. The actually mean age of all American football players is 26 years old, and the standard deviation is 3.3. Okay. So again, yours were older. That's all right. Okay, just to give you an idea. And that is sigma. Sigma is 3.3. The population standard deviation is 3.3. And the population mean is 26. Okay, so it's very important that we know how to do all these different things and read these symbols. So we have mu for the population mean. We have X bar for the sample mean. But then we could say, what is the mean of the sample means? Does that make sense? And we could also say, what is the standard deviation of the sample means? So here's what we got. And this is a really important definition. We're going to be using it a lot. And that is the distribution of all sample means with the same sample size is called a sampling distribution of the sample means. So it's a sampling distribution. So again, that's an important definition. Because again, we had 37.3 and 29, but you can do this all day long and we can look at the distribution of all the sample means. And that's a sampling distribution. Any questions on that? Okay. So if you look at the population mean of all possible sample means, when we think of population mean, you usually use mu. When you think of sample mean, you usually use X bar. So typically, the notation people use for the population mean of all possible sample means is mu sub X bar. Now, that for a lot of you is really hard to figure out how to type. So if you were asked some question, you had to type in use of X bar. So on an exam, for example, I'm okay if you write mu and a little underscore X BAR, capital BAR, and then you know what you're talking about. Does that make sense? Otherwise, this is kind of hard to figure out. Okay, and in our class, I'll let you have that. If you're doing some kind of formal report, then you should always do it in fancy symbols because you can look it up and figure it out. But if you're doing a test where you don't have much time, then mu and then the subscript and the next bar. Any questions on that? Okay, so the population mean of the sampling distribution, that was mu sub X bar. The population standard deviation of all possible sample means, well, population standard deviation, we think of as sigma. And it's of all possible sample means, that's X bar. So sigma sub X bar is the notation we're going to use for the population mean of the sampling distribution. And it's okay if you write SIGMA underscore X capital BAR. Any questions so far? Okay, so that is giving us a new type of data. So now the data are the sample means and not the individuals. Okay, so that's what we're going to be looking at. Okay, and just let you know, there's such a huge sample size for almost any situation that you can't list them all. Okay, and in fact, you can't know mu sub X bar and sigma sub X bar by looking at them all because you can't get them all. Okay. Also, again, sigma sub X bar, that we said was the population mean of the sampling distribution because it's so important. There's a phrase that people use, and that's called the standard error. So the standard error are two words that you use for sigma sub x bar. So a little bit of language today, not too much, and then there's some notation too. Any questions on the language or the notation? Okay. All right. So the sampling distribution for a statistic for samples of size n is the distribution of all possible sample statistics from samples of size n. That's my second time saying it. All right. So this is important. Okay. A statistic is an unbiased estimator for a parameter if the mean of the sampling distribution for that statistic is equal to that parameter. Okay, that's a lot of words. Okay, so the idea here is you have an unbiased estimate if you looked at all possible samples and you looked at the estimate from each of the samples and you looked at the average of all the things you could get, will that equal the the statistic that we're looking for? Okay. So the one really important one is the sample mean. The sample mean is an unbiased estimator for the population mean. Okay, and that's assuming that your sample is unbiased, that you're not just picking your favorite people. Okay. So for example, if we looked at all possible samples of size 3 of football players, and we looked at those averages of the three, of the next three, of the next three, of the next three, et cetera, and then took the average of all those averages, you're going to get the population mean, which makes sense, doesn't it? That you should get that. So the sample mean is an unbiased estimator for the population mean. So if you do a sample and you look at the average of that sample, that's kind of your best guess. If that's all you've got is that sample, your best guess would be the average. Okay, or the mean of the sample, your best guess for the mean of the population. Any questions? I hope I'm not losing you because there's a lot of language. Okay. If it's not an unbiased estimator, we call it a biased estimator. Can you think of a biased estimator? Again, the sample mean is unbiased. Can you think of an example that's a biased estimator? Don't see everyone jumping in. Okay. Okay, convenience sampling. So in the unbiased or biased estimator, that's assuming that that the sample is a good sample. It's a random sample. So, so let me give you an example. I think you'll agree that I think it'll make sense to you. Let's look at the example we just did, which was ages of um, the three football players, the average age of the three football players. But instead of taking the average age of the three football players, let's look at the range. That's a biased estimator. So if you randomly pick three football players and look at the range of their ages, that is not a good estimate for the total range of all football players. Because the range of all football players is the oldest football player there is minus the youngest football player there is. And if you randomly pick three football players, you're never going to get anything close to that. Does that make sense? So the range is a biased estimator because the average of the sample ranges is not going to be the population range. Any questions on that? Okay. It turns out the standard deviation is slightly biased. If you have a very large sample size, it's almost unbiased, but it's slightly biased. If you have a small sample size, there's more bias. Okay, and that just trust me on that. That one's harder to see. But the range you should be able to see. Any questions at all on what it means to be an unbiased estimator versus a biased estimator? All right, you ready for the big theorem? Most important theorem of all of statistics. And it's called the central limit theorem. Really, really important. Okay. So here's what it says, and this is going to be the central limit theorem for means. And it's got parts. It's got two parts. Part one is the sampling distribution for sample means from samples of size n has mu sub x bar equals mu, and sigma sub x bar is not sigma. It's sigma over the square root of n. That's really important. Okay. And the second piece is that the population's distribution is normal, or if the sample size is large. You almost never know that the population's distribution is normal, but you know what your sample size is. So if you get a sample size over 30, which means 31 is the smallest, then the sampling distribution for the mean is also approximately normal. Okay, where have you seen this over 30 before? In our class. Very important, by the way. Where have you already seen me say over more than 30 for our class, for something else? Yeah, project requirement. The reason I made that the project requirement is basically if you don't have over 30, then you have pretty worthless data. So it is very important to have a large enough sample size. In our class, we always use over 30. Remember, this course is elementary statistics. When you get in, if you decide to take an advanced stats class, it's more complicated. I try to simplify it by always saying over 30. But 30 is not over 30, by the way. Okay? 31 is over 30. So that's important to note too. All right, so that is the central limit theorem. Let me show you a picture of it. I coded this up. Let's suppose we started out with a skewed left distribution. Okay? And let's suppose the mean was 297.96 and the standard deviation was 97.67. Then if we looked at samples of, say, size 100, we could look at the distribution of the sample means of samples of size 100. And what this program will do, it'll randomly grab a bunch of them and then draw a histogram out of it. And in fact, it randomly grabbed 2,500 samples, each of size 100. Great thing about computers is they're a lot faster than we are. And this is the histogram that was drawn out of that. Notice a shape. That shape is somewhat normal. It's pretty normal. Do you see? It's unimodal, it's pretty symmetric left and right from there, even though the original was definitely not normal. The original was skewed left. But here we have a pretty normal distribution. Okay, of our samples, the mean of those 2,500 samples was to two decimal places the same as what we started with, 297.96. Because the central limit theorem says that, hey, that's the population mean. And guess what? If you have a giant sample size like this, you can be very close to what the population mean is. Okay. The standard error, sigma sub x bar, was 9.86, which is not even close to sigma. But the central limit theorem says that the sampling distribution does not have the same standard deviation of the original. It has a standard deviation divided by the square root of 100. By the way, what's the square root of 100? It's not a hard question. Yeah, 10. Okay, and what's 97.67 divided by 10? Also pretty easy. Yeah, 9.767, which is pretty close to what this random stuff got. Do you see? And that's what's going to happen. It's never going to be exact when you have a sample size of size 100 and you take a bunch because you take an infinite amount to get exact. But we got pretty close, didn't we? 9.86 versus 9.767. Any questions on the central limit theorem, what it does? I just want to let you know that one great thing about the central limit theorem is if you have an approximate normal distribution like this, we can find probabilities because the normal distribution is a standard function and you have a calculator for the normal distribution. If you have a distribution you don't even know what it is, you can't find probabilities because you don't know what the distribution is. So the central limit theorem, if you have a large sample size, will allow you always to find probabilities. Isn't that nice? Okay, so you ready to see an example that's really important? Okay, any of you into finance or business or economics? Maybe not. Yes, no? Okay, even if it's not your major, someday you'll probably want to like invest money well. So I'm going to give you a kind of example. All right, let's do the easiest one. Suppose you put $10,000 into the bank. Okay. What is the probability you're going to end up losing money 1 year after? Okay. And the idea is losing money means the probability that X is less than zero. So that's the amount of money you made is less than zero. Okay. And the idea here is if you put money in the bank, you won't lose money. Okay. You may not know about our laws, but there's something called FDIC insured. So even if the bank goes bankrupt, the government will give you the money back. Um, so that probability of X being less than zero is zero. Okay. So this is very safe. On the other hand, the mean interest rate, and again, I looked at Google, asked Google a survey question, and it told me that the average interest rate for bank accounts, was 0.4%. Is that a pretty good interest or not? What do you think? Is that high interest or low interest? You making a lot of money off of it? I don't see y'all jumping in. Okay. 0.4% is tiny. It's a really small percent interest. Remember, inflation is a lot higher than that. So in terms of like real value of your money, you're actually losing in terms of value. Okay. You're still going to have more than $10,000, but not much. So are there any other choices besides investing by putting into the bank account? Can you think of something else you could do? Any thoughts? This is really important, by the way. Even if you're not going to be you're not going to major in economics, hopefully you'll have some money and you'll have to decide how to invest it, what to do with it. Okay, you can do business, and business is really hard in terms of the statistics, by the way. I'm not even going to go there, but stock. All right. Okay, so now let's suppose that you put your $10,000 into a randomly selected stock. Now, the mean interest, okay, or the mean amount per year you get on stock is 9%. And the standard deviation is 20%. Okay. Whereas for the bank account, the standard deviation is 0%, but it's a tiny mu. Okay, we're going to assume that stock market returns are normally distributed. What's the probability you're going to end up losing money? So now we can say x is approximately normally distributed. So x tilde n, 9 comma 20. Losing money means the probability that x is less than 0. And we got to find that out. And the good news is that's not that hard because we have a calculator for it. Okay, so we have a calculator for it. So let's go back to the calculator. This is last week's stuff, but we're going to use it for this week's also. Okay, so we want the probability that we end up with less than 0. The mean, I'm going to do it in percentages, the mean percent was 9%. The standard deviation was 20%. And we calculate. All right. So here it is. I'm going to round to 2 decimal places. So that's about 0.33. So the probability of losing money is about 33% chance of losing money if you invest in a stock. Okay. Do you think everyone is okay with a 33% chance of ending up losing money? Any thoughts? Yeah, a lot of people are not okay with that. That's a pretty high percent chance of losing, especially if this money is really important. Like if you need this money for your college education, and if you end up having less than 10,000, you have to drop out of college, then that's not okay. Okay, so here's another option. Have you heard of the Dow Jones Index Fund? Most of you probably heard of the Dow Jones. So the Dow Jones, by the way, has 30 stocks. So what is the probability of losing money if instead of investing in a single stock, we're going to take our money and we're going to randomly select, basically, and we're going to call it randomly selecting 30 different stocks, call it the Dow Jones Index Fund, and that's what index funds are about, is they, make sure that it's like a good sampling distribution with somewhat randomness in a way. Okay, we're going to assume the Dow Jones is a representative sample and that all stocks are independent of each other, which is not quite true, but we're going to pretend they are. So mu is still 9%. Sigma is still 20. And now n is 30. And 30 is not greater than 30, but since we're assuming that the stocks are normal, that everything's normally, we're allowed to use essential limit theorem and get normality. So we can say x bar, which is the mean amount of, in percent that you're going to get, is approximately normally distributed with mean 9. So again, if you look at the central limit theorem, mu sub x bar equals mu. So we had a 9%, we still have a 9%. But sigma sub x bar is sigma over root n. So what we're going to do is we're going to take sigma, which was 20, and divide it by the square root of n, or the square root of 30. And I put it in a calculator, 20 over root 30 is about 3.6514833717. Okay, wouldn't want to do it by hand. Calculator will do it well. Okay, so now, I think I wrote this, but I don't, just in case it's not right. So now we have a new standard deviation. Notice the standard deviation of the sampling distribution is much smaller than the standard deviation originally, which was 20. Now we're like 3.7 or so. So the standard deviation has gone way down. So now if I change that standard deviation to what we had, 3.6514833717, and recalculate the probability of losing money, now what do you notice? It's much smaller, 0.007 or so. Anyone lost on what I just did? Any questions? Okay, so now, would you be okay if there was a little bit less than 1% chance of losing money? Would that be okay with you? Yeah, most people would be fine with that. So you probably heard about the whole diversified investment thing because what that does is it uses the central limit theorem. Okay. And by the way, if you put money in the long term, then this really does work. Okay. Then this randomness works. Okay. If you do it for 1 month, everything could go bad. We've seen the stock market die at one, go way down in a month or something like that. Any questions on that? Okay. So if you diversify, you still have a mean of 9%, but now the probability of losing money is really small. Okay. But the probability of winning a whole lot of money will be small also. You're not going to get, 40%. That's not going to happen. Okay. You're not even going to get, 20, 15%. You're going to get something really close to 9%. Any questions on that idea? Okay. So, by the way, do you think I use this personally? What do you think? Do you think I use the central limit and statistics for my investments? Any thoughts? The answer is absolutely. And yes, I do pretty well in the market because I understand the statistics and it makes all the difference. Okay, I'm not a billionaire, but I have made money. Today was a good day. I made over $5,000 today in the stock market. So that happens. And we'll talk about other ways of making good money in the stock market too. Okay. Some days I lose, so. Okay, so suppose you want your standard error to be equal to 2. How big a sample size do you need? Any questions on the question? Okay. So to find that out, we use the central limit theorem that says the standard error, that's the sigma sub x bar, is sigma over root n. So that sigma over root n, we want it to be equal to 2. So sigma was 20 over root n is equal to 2. Just so that you understand the math a little better, I wrote 2 over 1. Hopefully you know 2 is the same as 2 over 1. And then I can cross multiply and I get 20 times 1, which is 20, equals 2 times root n. I divide both sides by 2 and I get 10 equals root n. Square both sides and I get 100 equals n. So if I want the standard error to be equal to 2, then I would need to have a sample size of size 100. Any questions? Any questions on how that calculation was done? Any questions? All right, so the next piece of the central limit theorem is a central limit theorem for proportions. And here's what it says. So first thing, just some reminders. We use P for the population proportion. Do you remember when we don't use the Greek letter like we did for means? And remember? Because the Greek letter for P is pi and everyone gets confused. So the world has gone to P for population proportion and a P with a hat on top of it, which we say P hat, and it's okay if you type P H A T, is the sample proportion. And we're going to use the letter Q for 1 minus P. So if you have a P% chance of winning, you have a 1 minus, if you have a P chance of winning, you have a 1 minus P chance of losing, right? Right? If you have an 80% chance of winning, you have a 20% chance of losing. Okay. So The sampling distribution for sample proportions from samples of size n has the following. Mu sub p hat equals p, which basically is saying that the sample proportion is an unbiased estimator because the mean of all possible sample proportions is the population proportion. Sigma sub p hat is the square root of pq over n. One thing to note is the n under the root is in the denominator, so we really have an over root n, just like we had before. So by having a larger sample size, whether you're looking at means or whether you're looking at proportions, by having a large sample size, you make sigma sub p hat smaller. You make your standard error smaller. Okay, and if the standard error is smaller, that means you have a better guess. Because hey, if you try something and this is what you got and you have a very small standard error, then it's very unlikely to be far away from it. So if you're going to be doing any kind of study, a larger sample size is going to make kind of a better survey or better results, more consistent results, more, happy. Hey, I know this is right. Okay, or at least it's really close to being right. Okay, and then second, NP. So if you take it, let's say you did a sample of 200 people, and 80% of all people would say yes to your answer. Then the way you find out how many people you'd expect to say yes is you take 200 times 0.8. And that's NP, the number in the sample times the proportion of yes answers. And that's the predicted number of yes answers. And NQ, by the way, that's the predicted number of no answers. Now, for our class, and pretty much standard, they both have to be bigger than 5. Then if they're both bigger than 5, the sampling distribution is approximately normal. Okay? So if they're both bigger than 5, the sampling distribution is approximately normal. Okay? Notice that with the central limit theorem for proportions, it's not that the sample size is bigger than 5, and it's definitely not that it's bigger than 30. It's that the predicted number of yes answers and the predicted number of no answers are both bigger than 5. So NP and NQ both have to be bigger than 5. So here's something I want you to put in the chat box. I want you to type in, word for word, I promise not to use over 30 when the survey is a yes or no question. Put that in the chat box. It might take you a minute to type, but I want you to type in this promise. You're making a promise. So if you have a yes, no type question, you're promising not to say, hey, I need over 30. So I promise not to use over 30 when the survey is a yes, no question. Put that in the chat box. There's a reason why I'm having you put in the chat box, by the way. Okay, I want all of you to type that in. Okay. Give me another 2 seconds. It shouldn't take long. It's just one sentence to type. Maybe I'm a faster typer than you are, but you can all type. Can you put in the chat box? Okay. There's a reason I'm having you do it, and that is this is one of the most common mistakes that students make. So I'm hoping by putting in the chat box as a promise, you will actually keep your promise. Okay? Because otherwise it's just wrong. Okay? Any questions on that? Okay. If it's think about the survey question. If it is qualitative, So if it's not a number answer to the survey question, then don't even think about over 30. It is the number one mistake. And by the way, if you're watching this online, write it down on a piece of paper. Just promise or yell it out to make that promise so you don't make that mistake. It's such a common mistake. Okay. And by the way, I see a lot of people just have too small a sample size, and then you can't really do anything statistically, and they do anyway, and it's just wrong. Okay. And sometimes I read articles and their sample size is too small, and it's like, no, don't even think about that. Okay. This is just a terrible idea. Okay. Sometimes it's former students that are now doing research for their master's degree, and their sample size is too small. Okay. I've even worked for the Forest Service. I've done some consulting for the Forest Service. I'm the statistics consultant for them sometimes. And they'll show me their data, and it's like, no, your sample size is too small. This doesn't work. You need to get a bigger sample size. Any questions on that? Okay, so here is a study I looked at today. I was like trying, do important stuff that's going on, and my guess is you've heard of AI. It's kind of taking over the world. So this is important. So in 2023, 10% of all workers used AI for their work. That's not long ago. Gallup surveyed workers at the end of 2025 and found 12% used AI for their work. If 10% still use AI for their work, what would the probability that a new sample with the same sample size would have at least 12% use AI for their work? Okay, I know this sounds a little complicated, but this is a very typical use for the central limit theorem for proportions. Okay, so let me go. And by the way, their sample size was 22,368. Okay, so let's look at finding this probability. So to find the probability, first we got to make sure the central limit theorem works. Okay, so NP is 22,368 times zero point 0.1. I'm hoping you don't need a calculator to realize that's a lot bigger than 5. 10% of 22,368 is like over 2,000. Much, much bigger than 5. And NQ is 22,368 times 1 minus zero point 0.1. That's even bigger than that. Much bigger than 0.5. So when you have NP and NQ both bigger than 5, we can apply the central limit theorem for proportions. Otherwise, you can't. Okay, next, we're going to look at our distribution. So p hat is approximately normally distributed. So the sample proportions, all the sample proportions, are approximately normally distributed because our NP and NP and NQ were big enough. The sample mean is 0.1 because we're saying, hey, if 10% still use AI for the work, that would mean that 10% would be our population proportion. And here, mu sub p hat is p, which is 0.1. So 0.1 for our sample mean. And then for our for our population mean. And then for our population standard deviation or the standard error, that's the square root of PQ over N. P is 0.1, Q is 0.9. 1 minus 0.1 is zero point 0.9, by the way. Right? 10% said yes, 90% said no. Divided by the sample size, 22,368, I popped that in my calculator and I got about 0.002. And I know this 0.5 should be 0.1. Sorry about that. Any questions on seeing that we have a normal distribution and finding the mean and standard deviation for the sampling distribution of proportions, of sample proportions? So now we can find the probability. Well, 0.1 and 0.002. So I go to my calculator. The mean is zero point 0.1. The standard deviation was 0.002. We want a probability, so I'm going to leave that blank. And we want the probability that at least 10%, I'm sorry, at least 12% of our sample would say they use AI for their work. So I want to say at least that's greater than 12% is 0.12. And I hit calculate. And notice it's basically zero. Okay, it's a tiny, 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 tiny probability. So what that tells us is there's a tiny probability. Okay, when it says zero, that means almost no chance. It's not truly zero, but it might be 100, might be point and then 100 zeros and something else. So it's zero close enough. So it's a tiny, tiny probability that if 10% of all workers use AI for their work, and if they surveyed a new group of 22,368 randomly selected workers, then there'd be almost 0% chance that at least 12% of them use AI for their work. Any questions on that? Okay, so if there's almost no chance that that could happen and it happened, what do you do? If there's like less than 1 in a billion chance that it could happen and it happened, what is it, at that point, what should you do scientifically? And this is going to be really important in 2 weeks, by the way. Kind of like the whole main point of all this. An idea? You go back and you say, well, was there something that we assumed that's not true? And what we assumed is that 10% of all workers use AI for their work. So when you have such a tiny probability of what we got happening, you say, well, something went wrong. What went wrong is that more than 10% of all workers use AI for their work. Any questions on that? And that's like the main purpose of the central limit theorem is to be able to make that conclusion, which we're going to do in 2 weeks, by the way. But there's a heads up. Okay, so next is going to be the central limit theorem for sums. And here's what it says. So the sampling distribution for the sample sums for samples of size n has, and I write this as mu sub, this is a little summation sign. If you've had a bunch of math, you've seen it. If you haven't, trust me. So it's mu sub sum of x. So it's capital sigma is the way you read it. It's kind of weird. Is equal to n times mu. And standard deviation of the sum of x is equal to sigma times the square root of n instead of divided by. Okay? If the population distribution is normal, or if the sample size is large, greater than 30, then the sampling distribution for sums is also normal. So note that that's very similar to what we had for the central limit theorem for means. It's really exactly the same. Number two is. Okay. We can also write this as the sum has a normal distribution with mean and mu and standard deviation sigma times root n. Where do you think you'd be more interested in the sum than the mean? Can you think of an example or circumstance where the sum is more important than the mean? Anyone can think of an example where you would care more about the sum than the average, than the mean. And another word for sum, if you don't know, is total. Total venue? When you say venue, what do you mean by venue? Because often that doesn't even represent a number, so I'm not sure. So when is the sum more important than the mean? Maybe you typed it wrong. That's possible. Okay, I don't see anyone. Let me give you an example. It's kind of the most common example for sums. Okay, and it happens really important when you have a business and you care about money, revenue. Yeah, maybe that's what you meant to write. Revenue. Yeah. So let's suppose that the average customer at a restaurant spends $33.23, and the standard deviation is $9.22. If 65 customers eat at the restaurant today, what is the probability that the total revenue for the restaurant will be less than $2,000? What is the first quartile for the total revenue for a day? Okay, so notice, by the way, this is an example where if you were the manager or the owner of the restaurant, it's the total that matters. It's how much money you made by the end of the day, not the average amount the customer is spending. Does that make sense? Okay. And you might care about less than 2000 because that might be your costs because you got to pay the employees and maybe you got to pay rent and all kinds of other things and food and all that. So you want to make sure you're making a profit. So this is an example where it's really important to be able to handle the total. So we jump right to the central limit theorem. And that is sub sigma x, sub capital sigma x is n mu, and standard deviation of capital sigma x is standard deviation of the population times root n. So we could say the sum is approximately normal. Okay. And by the way, we had 65 customers. That's definitely more than 30. So we take 65 times 33 for our mean of all possible totals, and then comma point, and then 0.23, by the way, 33.23, and then comma, you take 9.22 times the square root of 65. I popped that in my calculator and I got 2145, comma 74334. Any questions on that? Okay. If I want to find out what's the probability of getting more than 2000, then I go to my calculator. We want greater than 2000. Okay. And then we say the mean was 2145. And the standard deviation was 74.334. We want the probability. And there it is. So about a 97% chance. Okay. Now, that might be good enough for you. Okay. If it was a complete disaster of making 2000 or less, then that may not be good enough. But that's probably, 97% chance is a pretty good chance. Any questions on that? Okay, next, we're asked to find the first quartile. How do we find the first quartile? That's Q1, by the way. Another way of writing it. How do we find Q1? Yeah, now we know the probability of being less than some value, and the value is what we want, is 0.25. Okay, our mean and standard deviation are the same because it's the same central limit theorem. But now our probability we know is 0.25. We want less than a value. And we don't know the value, so I leave that one blank and hit calculate. So the first quartile will be $2,094.86. Any questions on finding the first quartile for this example? Okay, no questions? All right, here's the next question. I put this one in because a lot of people have trouble with this. And that is, let me hop it in without seeing the rest. Between what two values will there be an 80% of the sample sum lying between? Okay, that we have to do some thinking. Any ideas on how you might approach that? Between what two values will there be an 80% of the sample sum lying between? Okay, I'm not seeing everyone jump in. Okay, the idea here is we need to think about if there's 80% between the two values, then outside the values will be 20%. The left of the value will be 10%. So what I can do is find the 10th percentile. So instead of 0.25, I'm going to go 0.1. And it'll be less than, and I hit calculate. So one of the values will be 2,049 and about 74 cents. Nobody cares. People probably don't even care pennies, right? $2,050 is good enough for if you're a manager of a restaurant, right? You don't care about 27 cents. Okay, any questions on that? So the lower value would be 2049.73. For the upper value, well, that'll be 10% above it. So I'm going to hit above. And that'll be $2,240 and about 26 cents. Any questions on that? Big warning, it's a lot easier to watch me do it than to do it yourself. So we can say that 80% of all sums, sample sums, will be between $2,049.74 and $2,240.26. Any questions? Any questions on making this calculation? If I went too fast, please let me know. But I'm always happy to answer questions. Any questions? Okay, so we have now seen the central limit theorem. Central limit theorem for means, central limit theorem for proportions, central limit theorem for sums. One thing that people have difficulty is identifying which is which. So one thing I recommend is the very first thing you do is say, well, if I were to conduct that survey, what am I going to be getting? Am I going to be getting numbers or am I going to be getting like a yes, no type answer or two different possibilities only? If it's two different possibilities only or a yes, no answer, that's going to be proportions. Okay. If it's a number answer, then just see what are some of the key words. And if a key word, for example, here is total, that would be the sum. If the key word is mean or average, then that would be the mean. Any questions on kind of looking at that and seeing the difference? Because if you get mixed up on that, it's going to be a disaster for you because you'll get the whole thing wrong. Any questions on this idea? Okay. And by the way, the proof of the central limit theorem is brutal. We're not even going to think about it. I know how to do it, but you have to be, a high level math major. So we're not doing the proof, but you can trust me that it's true. Okay. Or you can go online, read a book or whatever. It's clearly true. Okay. All right. So One thing is that I try to make this week a little bit easier. How come? In terms of the chapter? Because I could have put chapters 6 and 7 together, but I didn't. Okay, the reason is you have your project due, and the project has taken a lot of work. Okay, and I want to remind you, do not use AI to do your anything on your project. Okay, nothing should be done with AI. Okay, I will know, and it'll be very bad for you. So do not use AI for your project. Okay, on anything in your project. Okay, ask each other, do not ask AI. You can also ask a tutor, you can ask me questions, you can post in the Project One discussion board, any question you have, and I'll help you out. Okay, but do not use AI. I will know, and you'll have a very low score on your project. And the other is make sure you have partners. You can't pass without partners, basically. So what I have next is the secret word. Okay, although it's not technically a secret word, it's a number. 31. Why is the secret word 31? Why is the secret word 31? And why is the number, don't type it THIRTY or ONE or something. 31. So why is the secret word 31? What's important about the Yeah, that's the smallest sample size you can have to have good data when you have quantitative data. So don't even think about 30. 30 is not good. Okay. If you only surveyed 30 people for your project, then I zap you on it. If you 30 survey 31, then that's good enough. Any questions on that? Okay, so that's pretty much it for this webinar. It's a little shorter than usual because I want to make sure that you have time for your project. Next week will be a little longer, possibly, because it's harder material, but there won't be a project to worry about. So I'm going to stop the recording.